Hey, we're going to be continuing with our Gauss's Law problems in our electricity and magnetism module. So far we've covered infinitely long rod, infinite plane, we've covered a point charge, a solid non-conducting sphere, a solid conducting sphere, we've covered a spherical shell, a spherical capacitor, and now we're going to move on to our last one of this list, which is our cylindrical capacitor. So if you want to see any of the other videos, I'll just put the links on that sheet to the side there. And as I'm talking, you should be able to just go ahead and click those. So for this video also, just note that our lambda as our charge per unit length, as we have here, is actually going to be noted as a lambda with a superscript plus for our positive charge per unit length, and superscript minus for minus our charge per unit length, which is just for the rod and the outside there. So what we're going to do is we're going to have a look at this, and if it's not too clear from a drawing, I'm just going to explain what we've got here. So we've got an infinitely long rod basically in the centre of some thickness A, and this has got a positive charge on it. We have a shell around that with some thickness, which is the difference between B and C. And this goes on, and both these go on for some distance L, which we're going to be looking at, but they're infinitely long. And this has a negative charge on it. And this negative charge per unit length is our lambda minus. And inside we're taking a Gaussian surface there of some distance r. And our length A is from the centre of this to here. Our length B is to the inside of the outer shell, and length C is to the outside of the outer shell. You'll sort of get what's going on as we go across. So we're dividing this up into 4 surfaces which we're going to take. So our first Gaussian surface is inside where r is less than a. Our second Gaussian surface is the one we've drawn here, which we'll need to calculate mathematically. Our third surface is inside the negatively charged conducting surface. And finally, our last one is outside of everything. So for our first one, as we discovered in all of our last videos, we know that this is conducting, so when r is less than a, our electric field must be 0. So this is our electric field for our surface 1, is 0, which means also for our third surface our electric field there must also be 0 because that's also conducting. I probably shouldn't write it like that, it's technically incorrect. We'll say this is equal to E3 and E1. And then for our other two, so we're going to need to calculate our second surface, which is the one we've drawn. But for our fourth surface, we can actually look at this and say, well, we'll do our fourth one first. This is nice and easy. And we say we have our Q enclosed over epsilon naught, which is equal to our integral, which we have here by E4 dot dA there. But our Q enclosed over epsilon naught, this is equal to our lambda by L, this is our L, and it's our positive lambda plus our negative lambda all over epsilon naught, which is equal, now these two are the same in magnitude but opposite in charge, so this is actually 0 then over epsilon naught, therefore means e to the 4 equals 0. So that one's 0 as well. And that's just basically because if we have some charge inside for our capacitor and the same but opposite charge on the outside, those two charges are going to completely negate each other, and that means that our Q enclosed is going to be 0, which means that our electric field must also be 0 because now we have no actual Q enclosed, as we know from Gauss's law. So that's nice and easy, and now we can just do our surface 2, which is the only one we have to solve mathematically. So we'll deal with our integral like we do every time. So you have our E dot dA. Now, to get rid of the dot product and the vectors, we insert our cosine of theta. So E dA cos theta. Now we know theta is 0. So we know that cosine of theta is 1. So we just get, which is equal to E dA, which means we can take E outside, and we're left with just the integral of dA by E, and then we know the integral of dA is just going to be A. So what we find that we're left with is in fact EA, and this is equal to our Q enclosed over epsilon naught. Now our Q enclosed is going to be, at this point, only our positive charge is enclosed, and that's our charge per unit length by our length is going to be our positive Q. So this is our lambda plus by L all over epsilon naught. Now what's our area? Now we're going to move on and we've got to solve for our area. So if we're going to find our area, and we look at this and we say, we can take our length as one side, and we take our cylinder here, and we sort of unroll our cylinder and make it out flat. So when we unroll it, we get one side of our cylinder is going to be L, and then this side here is 2 pi r. This is the bit which we unrolled round. Imagine you close that back round again, you're going to have a cylinder. So A is 2 pi r L, which means that we can now rewrite what we have here, and we have E 2 pi RL. I'm sure you can see where this is going now, is equal to our lambda plus L for epsilon naught. Get rid of our L's on both sides, and you find that E is equal to positive lambda 2 pi R epsilon naught. Which, if you go back to the video for our infinitely long rod, you'll find that that's what we have there, so we just denoted it as just a regular lambda because we didn't have two different charges there. Yeah. And finally, what we're going to do is now we'll just graph this, and we'll say that what we're going to find as we go along to some point here, which is A, and then when we reach A, we're going to have a 1 over R dependence coming down, and then we're going to reach B. So B's there, where now it's 0, and that's going to go across all the way till we reach C, where it stays at 0 and just carries on at 0 forever. And that is how we find our electric field for a cylindrical capacitor. So just to recap over that, just to make sure you've got everything, but it's not really the maths that matters, because you'll be able to do the maths fairly easily. It's just sort of your theory of it. So up to where R equals A, it's conducting, no electric field. When we get outside of our rod, we find it's the same as just an infinitely long rod, because we have the same Q enclosed, because it's our charge per unit length by length, but our length becomes irrelevant as we find. And then as we reach the next conducting surface, we get 0, and then when we're outside once more, our two charges negate each other, so then of course our electric field must be 0 once more. So if you want to see my last video, my next video, or just a few more, you can go ahead and click there. And once more, if you want to see any of the other videos, just go ahead and click there now.